Hello friends, welcome to this lecture series of oscillations. In the last lecture, I have introduced the concept of oscillations and I have discussed the difference between oscillation and periodic motion. Now today, I shall start the simple harmonic motion or simple pendulum. I shall try to construct the equation of motion of this motion. Now let's start. Now a simple harmonic motion is also called free motion or free vibration. Why it is called free vibration? Because it is free from any resistive force, that is the damping force. So as a result, the amplitude and time period of oscillation remains constant. This time period depends on dimension and also elastic constants of the string or spring. So the period of this free vibration is called the free period. Now this is the picture of a simple pendulum or pendulum basically. Now the mass of this bob is m. Now if I displaced it from its mean position of the this stable position by delta amount of angle, then due to this weight of this mass, two components will be acting on this mass. One is mg sin delta, another is mg cos delta. Now this mg sin delta is basically the restoring force. So when this mass oscillates, the restoring force tries to keep the mass towards the mean position. And the negative sign actually indicates the direction of the restoring force. It is opposite to the displacement of the mass from the mean position and towards the mean position. Okay, and this mg cos delta we can equate to the tension along the string. So this is that string, this is the length of the string, and this string is inextensible string. Okay, now why this is called a harmonic motion, right? So the restoring force here you can see this is sin delta. So sin delta is basically a harmonic motion. Why? Because if you change the delta, this angle, after certain angle, the sin delta repeats its value. You can see here. So at 0 degree, the value is 0, and at 360 degree again the value will be 0. So after certain angle, it repeats its value. So that's why this is called the harmonic motion function. Okay, and that's why this motion is called the harmonic motion. Now as the mass oscillates about this point O, the torque of this force, restoring force about this O point will be what? Mg sin delta minus mg sin delta L. Okay, so this torque is actually tries to bring the mass back towards the mean position. Now the torque of this force T tension about O will be 0 because it intersects this point O, right? Now if we expand this delta, sin delta function, this will be like this, and if the delta is very small, sin delta will be delta, and this restoring force we can write like this. So here this k is basically mgl. Now as the delta is small, the displacement will be linear, and we can write like this, x proportional to delta. So F force, this force will be basically minus kx, because this sin delta is delta and x proportional to delta, so F will be minus kx, right? So thus the restoring force is directly proportional to the displacement and acts in the direction opposite to that displacement. So this is called the simple harmonic motion, as you know, and the pendulum is called the simple pendulum. Okay, So now let's see how to construct the equation of motion, and from there how to find out the time period of the simple harmonic motion. So as you know, tau will be like this, minus mgl delta, and that is minus k delta. So if the moment of inertia of the mass about an axis passing through this point O, I, the moment of inertia if it is I, the angular acceleration we can write like this, alpha, that is basically tau by I, okay, and that will be minus k delta by I. So this acceleration will be basically minus omega square delta, where omega is root over k by I, that is the angular velocity of this motion. So this is the equation of motion of angular simple harmonic motion. Now in terms of displacement, the equation of motion can be written like this. So this is the force, mass into acceleration, that is the restoring force, minus mg sine delta. So it becomes like this. Now as delta is small, the displacement is linear, so x is L delta, right? From here we can do that, L delta. So here if you put this, sine delta is delta, and then it will be x by L, and we get d2x dt2 equal to minus g by Lx, then minus omega square x, and omega will be root over g by L. So the time period of oscillation will be 2 pi by omega, right? Here we are getting one single frequency, because this is the simple harmonic motion, and the frequency will be like this. So it depends only on the length of the string, so dimension of the string, right? And if we consider a spring in that case, even another case, so the time period there it will depends on the elastic constants. Okay, here actually you can see this k here. Okay, so if we increase the length of the string, the time period will be more. Okay, so this is the equation of motion we are getting here. We have constructed for this simple pendulum, simple harmonic motion, and to know the form of the x, what will be the solution of this equation, so that we will discuss later. Okay, so thank you for today. Thanks.